Hello there, ATS 315 students, Dr. Shragi here, and we're ready to take on what I would say is the second biggest challenge of this course, and that is objective analysis. Now, objective analysis is an important topic in meteorology. In fact, there are whole courses on the curriculum at the graduate level about how to do objective analysis and how to, why and what kind of applications and so on. We are just kind of nibbling at one little piece of the objective analysis problem in this class. Let me kind of set up what the nature of the problem is. So far, you have something that looks like this. Hopefully, now that you have gotten, I guess it would be assignment 12 working, you are able to see that you have at any given time in your data set, you have observations from randomly scattered stations. I mean, they're not random, but they have nothing to do with meteorology, right? Where is Omaha? Where is St. Louis? Where is Sioux City? Where is Des Moines? You have these sort of randomly distributed stations. And what we're trying to get to eventually is plotting contour lines on there. And that's going to be our final assignment in the class. But here's the deal. When humans contour plots, we can do this. We can take a map like this map of temperatures here, and we can draw contour lines on them. You learned how to do that in even ATS 114 lab. But that's a real challenge for a computer. In fact, for all intents and purposes, it's impossible for a computer to draw contour lines based purely on randomly distributed stations like this. Rather, what the computer does is, or a computer program or an algorithm or whatever you want to say has to do, is it has to actually convert those randomly distributed stations that are just at a whole bunch of different possible latitudes and longitudes and convert those observations into a grid where we have rows and columns of data. Turns out computers are much better at contouring data that are on grids than if they are randomly distributed at all over the place. Even though humans with their eyes can easily contour data that is not on a grid. So this process of converting data that is on a 2D grid, that is just on randomly distributed points. You have a list of stations at these latitude and this longitude, here's its temperature. You know, the kind of things that you're getting from the current_SAOWXP file. And converting that to a two-dimensional grid with rows and columns of temperature or pressure or wind speed or dew point or whatever is one of the things that is part of this broader subject called objective analysis. Objective analysis is more broadly about taking irregular observations and interpolating and things like that. But the specific challenge here that we have to get to is in order to write a program that's going to be able to draw contours, we're going to have to be able to take the observations that are in the current_SAOWXP file and convert them to a uniform two-dimensional grid of data. Now these grids, you know, with rows and columns, think spreadsheets, think tables. Well, of course, this is an array. That's the terminology. Now you guys are all in the energy class as well, so working with arrays of data has become kind of second nature to you, where you have these ideas of these rows and columns of data and so on. Now, in general, when we're just kind of thinking about this, just to kind of make sure we're focusing on the C aspect, not the octave aspect of arrays, remember that arrays will have, these two-dimensional arrays will have both rows and columns, and the indexing of the arrays starts at 0. There's a row 0, and there's a row 1, and a row 2, all the way up to row number of rows minus 1. And the columns start at 0, and then 1, and then 2, all the way up to number of columns minus 1. And so, like, for example, this little array that I have up here on this on the screen here would be declared, since these are floating point numbers, we would have had to declare this as, like, let's just say temp, being my name for this array. We would have had to have declared this as temp, square brackets, 6, square brackets, 6, because there's 6 rows and 6 columns. Now, you have already worked with arrays in assignment 12, as well as other places along the way in the semester. So, like, you know, for example, that you could have done something like you could print the value at row 2, column 1, or you could have set the value at row 0, column 5 to 21.1, whatever. You can just work with individual elements of this array. In something like octave, we could do things to the whole array, like multiply the whole array by 2, or transform the whole array somehow, or compute the correlation from one column of the array to the other. That's all fancy schmancy stuff in an interpreted language like octave. In C, we basically can just like do math on individual elements of this array. Now remember, when we're working with arrays, just like we did in octave, just like we did in assignment 12, Generally speaking, we take the first index of a two-dimensional array and we call that rows. And we have a second index in the array and we're going to call it columns. So like if you are on this particular table here, if you had value 2, 0, that would be that value negative 2.3. It's in the column labeled, I'm sorry, the row labeled 2, which is actually the third one down, and column 0 is value is negative 2.3 in this case, okay? It, in fact, doesn't really matter. You can actually work with arrays the other way as long as you're always consistent. But in meteorology, we almost always do it rows, columns, where rows are the first index and columns are the second. And frankly, it's virtually impossible for me to help you find the bugs in your program if you switch this around. It just doesn't work. Always stick with that pattern of the first index is rows and the second index is columns when we're working with like an array of temperatures that are going to be on a map that eventually we're going to contour. Okay, and again, I mean, you saw how to work with arrays like in assignment 12. You don't need to get just too bogged down in all the details of this, but you know, for example, I want to show you this pattern here where like if I have a value already called num rows, that is how many rows are in my array, and let's just say num cols, that is the number of columns in my array. See how a little nested loop will work us through all of the values in the array? So like I will be what row I'm in and j is what column I'm in. And so I'll go on each row, I'll go through all the columns, and then I'll do the next row, and I'll do all the columns there, and the next row, and all the columns. This idea of using a little nested array to go through all the rows and all of the columns of an array, that is a hugely powerful tool. Make sure you understand what's going on this slide. If you have questions about it, let me know. See how this would print every value in the array? Okay, because we're going through each row, row I, we go through columns j, where j goes from 0 to less than num cols. And we just do that for all of the rows from row 0 to row less than num cols. All right, num rows rather. Make sure you understand what that's all about. Okay, next, let's talk about the challenge of objective analysis itself. Now, here's the deal. You are not actually going to write a function that does objective analysis. When I have graduate students in this class, I do make them do that. But instead, when I have undergraduates, what I do is I provide them with a function. You're going to see in just a little bit, there's a function called barnes.c. You'll see why that name is in just a minute. Here's the deal. Someday you're going to be off at a job someplace, and you're going to be working on some aspect of meteorology, and they're not going to expect you to reinvent the wheel every time something comes up. You're going to be part of a team who's using research and who's working with collaborators and so on. Someone giving you some code and saying, do something with this, this works, use it, is a thing you're going to do. Just like in the clipping function a couple weeks ago. I didn't make you reinvent the wheel on the clipping function. That's crazy. Somebody's already done all that work. So in this case, I decided at the undergraduate level, I give you a function called barnes, which is the objective analysis function that we're going to be using. You just have to use it. But just using it, figuring out what do you use for input, what do you get for output from the barnes function is complicated enough. We don't need to get just to push any farther than this. So for your program, you're going to be just using the barnes function, as I'm going to show you later in the second half of this presentation. But on like the next written exam and so on, you do need to understand how it works. Like what is objective analysis? How is it? What is the thinking behind how it works? And so that's what this part of the lecture here is about. Okay. So you won't actually be writing the barnes scheme from scratch, which is the objective analysis scheme that we're using here, but you'll be showing that you have an understanding of how it works. Because there's a whole lot of similar techniques in meteorology. Yes, you'll not be writing the objective analysis barnes scheme right now, but you will be doing something like that someday in your career. Well, there will be some kind of analysis that you'll have to do that is very similar. So let me show you what's going on here. Here I have a map of temperatures very similar to what you've been doing in assignment 12, okay? And what we want to get is instead something like this, where instead of having the temperature at each station, which could be wherever, instead we have a certain number of rows, we'll call that num rows, and a certain number of columns, we'll call that num cols, and we will have a value associated with each of those, and they're at some location. Each one of them is at some latitude and some longitude, and they're on a nice fixed grid. They line up north, south, east, west. Now, in this particular plot, because my map has a strange projection, they don't quite look straight north, south, east, west, but they will be in your program, as you shall see. How do we get from one to the other? How do we get from the irregularly spaced, the right word is sparse, the sparse station data, sparse means they're not evenly spaced, to the regular rows and columns that have been objectively analyzed. So I've put both kinds of observations on the same plot here. In green I have plotted the stations, and in blue I have plotted what we get from the Barnes objective analysis scheme, where they're nicely now on rows and columns. How did we get from one to the other? Well, before we think about how we got to this whole grid, let's think about just one point. I mean, if I just sort of zoom in on Nebraska and South Dakota here, let's just pick that value right there that I highlighted with a box. So someplace in southwestern South Dakota, my Barnes objective analysis scheme apparently decided that that row I, column J of my array, there is some temperature that is basically 65 degrees. Based on the temperature observations around it, the Barnes objective analysis scheme decided that the temperature there at that station, a good approximation, a good estimation of the temperature there, is 65 degrees. How did it do that? Well, it probably took into account the temperatures near that station. I mean, for example, here's a station in northwestern Nebraska, I don't know if that's Shadron or Harriman or something like that, and it's 73 degrees there, 73.9. That is a very close station to that grid point that we're trying to compute the temperature for. But, you know what, there's other stations nearby too, like that's, I think that's Spearfish, that might be Rapid City, I don't know, up there in South Dakota, that is not terribly far from our grid point either, and it is 59 degrees there. Can you see that the objective analysis scheme understood that there were two stations nearby? One was almost 74 degrees and one was 59 degrees. It clearly had to be, the temperature at our grid point clearly had to be somewhere in between that. Okay? How did it come up with 65? Did it take other temperatures into consideration? We'll have to keep figuring that out. I mean, maybe it had to also take into account the fact that it was currently 61 degrees at Valentine. Maybe. Okay, I mean, although Valentine's getting to be a little bit farther away, or maybe like, I think that's Scotts Bluff, it's 71. Maybe it had to take into account the stations in a big area around there to kind of come up with some area average. And in fact, that's basically what it did, is it kind of cast a net around stations over some area around it, centered on the grid point that we're working on right now, row I, column J. Centered around that, there is sort of a net that we have cast. And we're saying, hey, what stations are in that area? And you can see that it includes things like Scotts Bluff, Valentine, Shadron, and Rapid City. So, okay, probably those four stations are the ones that it considered. We could have had a bigger or smaller radius of influence. Let me go ahead and come up with this term here. The radius of influence will be how big of an area, how far away from our grid point we're willing to cast this net to see how many stations we have nearby. Okay? We have a radius of influence. You'll see that term several times in this Barnes scheme here. That's something we set. We could make the radius of influence smaller and have a smaller number of stations influencing the temperature at that grid point. Or we could cast the net wider and have a larger number of stations over a broader area influencing what we think is the temperature at that station. That's something that we have to decide. Now, if this was ATS 6, whatever it is, objective analysis, they would actually be learning the math of how you determine what is a optimal radius of influence. That is not what we're doing right now. We'll probably just use a radius of influence that I'll give you. But it is a certain distance, and we certainly could have had a smaller radius of influence, where it maybe as few as one station was actually inside the radius of influence. We could have had a giant radius of influence, where lots of stations, I mean, it's a little hard to see how that station in, that grid point in southwest South Dakota should be influenced by these places in Colorado and so on. But maybe there's a reason why we would want that. Maybe we would have to decide what is an appropriate radius of influence. Okay, so once you have this radius of influence defined, you have decided that you're using a certain number of kilometers away from your station, anything that's within that radius of influence. Now in practice, by the way, we're going to do it in terms of degrees, like how many degrees of latitude and degrees of longitude we're willing to be away from our station. But whatever, you could have done it lots of different ways. We've got two questions we have to answer. how do we know whether or not a given station is inside the radius of influence? And what are you going to do with that observation if it is inside the radius of influence? Now again, remember, you are not writing this code yourself. You are getting the Barnes objective scheme, but you will need to answer questions about how the Barnes objective analysis works. Again, also there's a chapter in the book that will be helpful to you. All right, let's focus on that first question there. How do we know if a given station, look, we're reading through the current underscore SAOWXP file. You can picture how this works, right? You are reading through the current SAOW, you just got a station. KOMA, Omaha, okay? How are we going to decide if KOMA is inside of this grid point's radius of influence? Remember, every grid point we're going to have to do this at. Ooh, boy. How are we going to do that? Well, we're going to have to figure out what is the latitude and longitude of that grid point, and then we'll have to look up on the SAOEZ city file what is the latitude and longitude of our station. Okay, if we know the latitude and longitude of our grid point, and we know the latitude and longitude of the station, we can find the distance between those stations. Now, we're actually going to do it in terms of degrees, but we could have done it in terms of kilometers or something like that. That would have been okay too. If that distance turns out to be less than the radius of influence, then apparently we are inside of the radius of influence. Slick, right? A simple little trick like this. We're just going to be going through, as we go through every grid point, at every grid point, that one, that one, that one, that one. At every grid point, we're going to have to actually do the math. At every grid point, we're going to have to check every station that came in at current underscore SAOWXP. Every single one of them will have to compute that distance between the latitude and longitude of that station and that point, and decide if it's in that grid point's radius of influence. Wow. Good thing computers are fast. Yeah, this will go pretty fast. I mean, I don't know. It might take a second or two for Chesapeake to do this math. When you think about how fast Chesapeake is, that's a lot of math it can do in a second or two. All right, now remember, the second of the two questions we had to ask ourselves is, what are you going to do with those observations? You've now cast this net around your grid point. You're doing every grid point, every row, every column. But right now, at row I, column J, you have cast a net of some radius, the radius of influence, and you now have, these are the stations that are inside of the radius of influence. And let's say you're computing the temperature, you want to figure out the temperature at that grid point. What are you going to do with them? What are you going to do with these? Okay, I've got a list. Inside of my radius of influence is Rapid City, Shadron, Harriman, Scottsbluff, and Valentine. Okay, well, now what? What am I going to do? Well, there's a lot of things you could do. Maybe you want to just take their average. You know, the average of the stations that are inside the radius of influence becomes your point. That would be a type of objective analysis. It just doesn't have very good properties. There's a number of reasons why the average would actually be kind of a disaster. See, the problem is, if you think about your radius of influence, the area inside your radius of influence is mostly far away from your grid point. The area near the grid point is small compared to the area far away from the grid point. If you just took the straight average of all the stations that are inside your radius of influence, the problem is most of those stations are pretty far away. Okay, so that their temperature doesn't necessarily have very much to do with what the temperature at the grid point is. So you kind of want to use some sort of weighted average, where somehow or other you're giving more impact or more weight to stations that are close to your grid point, and less weight to the stations as they get farther and farther away from. You still want them to maybe have some ability to affect the value. You don't want their weight to be zero, but you want them to be less important in determining the overall value of your temperature at your grid point. I mean, in this case here, the temperature at that grid point really ought to be closely related to the temperature at Shadron, because it's just not that far away. On the other hand, the temperature at that station in northwestern South Dakota shouldn't really have that much to do with it, because it's really pretty far away. Okay? On the other hand, at least it's still inside the radius of influence. I mean, the stations in Minnesota or Missouri or whatever are too far away. They have no impact on the value at that grid point. So what we need is some kind of weighted average that gives more weight to the stations that are close to our grid point and less weight to the stations that are far from our grid point. And that's a thing. Now, in practice, one of the standard ways to do that is this so-called Barnes objective analysis. It's an algorithm that can be used that computes weights for every value inside of the radius of influence depending on their distance from the grid point, and then computes an appropriate weighted average that, if there's some stations very close to our grid point, they get more weight, and the stations that are farther away, they get less weight. And it can be proven that this is a very optimal way for certain kinds of objective analysis techniques. The math behind it is, I said on the slide here, pretty complicated. I'm not sure pretty complicated is the right way to put it. Let's say it's not trivial, okay? And so instead, I give it to you, okay? You get the Barnes function. I have no problem giving you Barnes objective analysis as a file that you just need to implement. You need to be able to answer questions about what objective analysis is and what's the ideas and what's up with the radius of influence and all that kind of stuff, but you do not need to invent that. If grad students, yeah. Undergrads, no. The name of the file that I'm giving you is home shruggy j Barnes C. Okay, Barnes, notice there has an E in there. It's not Barnes like barns that pigs live in. It's Barnes as in a guy's name. And I'll give you that code. You just go get it. I've already got it set up for you on Chesapeake and everything. You can just go get it. And the name of the function that's in there is called Barnes with a capital B. And the Barnes function, just getting this to work inside of your program is going to be a big job. Let me just be very clear about one thing. Because the Barnes objective analysis is something that will happen one time in your program. You will have already done things like read the SAO Easy City file. You'll have already done things like read in your current underscore SAOWXP file. You now have all the observations. You'll have drawn the map and so on. Now it's time to do the Barnes objective analysis. Do it one time. It cannot be inside of a loop. If you put the Barnes objective analysis inside your loop, your program's going to run forever. Because even though the Barnes scheme itself takes only a few seconds to run, put it inside of a loop for like all rows and all columns, you'll be sitting there all day. The Barnes objective analysis needs to happen only once. And then you'll use the output of the Barnes objective analysis, which will be grids with rows and columns of temperature or pressure or winds or whatever it is you gave as input. And then you'll, plot those on the map, put the numbers on the map or whatever. Or, later in assignment 15, you'll contour them. Now, Barnes objective analysis is a complicated function that has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 parameters, arguments to it. We haven't done anything that had that much before. It requires that there are two defined constants beforehand. If you go take a look at the Barnes objective analysis function, that barnes.c I gave you, up at the top, there are two constants already pound-defined up there. Pound-defined num rows and num columns. That are going to be how many rows and how many columns are going to be in your output grid. I have them there at the top of the barnes.c stuff, but that's probably not where you want it. You probably want that num rows and num columns to be at the top of your main program. Up there where you have like the pound includes and things like that. Because you also need these values, num rows and num columns, in your main function, as you're going to see. So I put them there at the top of Barnes just so that you don't forget them, but when you take a look at Barnes, oh yeah, that's right, that has to be there. But right away, delete them off the top of the barnes.c function that I'm giving you and put them at the top of your main. There's good values and bad values to use for the number of rows and columns. I think I suggested, both in the book and in at the top of barnes.c, I think I suggested 25 rows and 37 columns. They don't have to be that, they could be, but I mean, that's a good idea of like the ballpark. Okay, don't make yourself have 100 rows and 100 columns. Don't make yourself have 2 rows and 2 columns, okay? You want to be on the order of like 2 dozen rows and 2 to 3 dozen columns or something like that. That'll be enough that your contours will look nice, but not so many that the program takes forever. Because again, it scales. I mean, if you have 10 times as many rows and columns, you'll have 100 times as many grid points. The program's going to take 100 times longer. Okay? So, yeah, use the values that I give you there. Okay. Now, there's a whole lot of things that go as input into the Barnes function. You will be creating these different arrays and so on before you invoke the Barnes function. You will be filling these different input arrays up with the necessary data before you invoke the Barnes function in your C program. The first one I called ID. You don't have to call it ID. It can be called whatever you want. But they are the station identifiers that you have read in from the current underscore SAOWXP file. So when you read in the current SAOWXP file, instead of like reading a station identifier and doing something, just reading a station identifier, now store them. Okay? Make yourself an array. It needs to be declared to have 10,000 rows and 10 columns, where it's a set of strings that are up to 10 characters long, and there's up to 10,000 of them. Okay, I don't think there are anywhere near 10,000 observations in the current underscore SAOWXP file that you guys have been working with, but I've got CDs here with other SAOWXP files. We could, work with some fresh new data or something like that. 10,000 is a good upper limit. You won't ever overrun that. There's never more than 10,000 observations in an hour, so that's no problem. So you need to have declared a set of 10,000 strings like this. It doesn't have to be called ID, but those are when you are reading through your current underscore SAOWXP file, store the station identifiers there. Use string copy to put the station identifier that you're reading into each value of this array. So you read the first station, let's say it's KOMA, put KOMA into character ID 0. ID 0. But then your next station, let's say it's Norfolk, KOFK. Put that KOFK into the second value of ID. Fill that up, because when you pass it to the Barnes function, it's going to need that information. That's how it's going to know this is my station, and then more information coming. Now, your second array that you're going to send off to the Barnes function is the one that actually contains the sparse observations of whatever parameter it is you're plotting. Like in this case, I just called it temp, because maybe it's temperature or something like that, but you could be calling it whatever you want. But it needs to be declared to be 10,000 floating point numbers. That's what the Barnes is expressing. Doesn't mean you actually have 10,000 observations. I mean, someplace farther down here, we're going to be telling it how many stations observed this hour. That's fine. But you need to have room for up to 10,000 observations that came in this hour. So these are going to be the observations that came in on the current underscore SAOWXP file. So like when you decoded temperature code, instead of just sort of having this value tempf, put it into this array, into the row that you're working on right now. So if row I is KOMA, put your temperature at KOMA into that same row I. Okay? Great. Okay. So the first two arguments to this Barnes function are things that come from the observations. The list of stations that reported this hour and the data that you want to perform a Barnes objective analysis on from the observations this hour. Those arrays have to contain 10,000 elements. Doesn't mean you necessarily have used them all, but because of the way C handles memory and things like that, you had to in advance tell it won't be bigger than this. And so there will be 10,000 elements in those arrays. Okay, the next three arguments are going to be coming to us from data that we read from the SAO Easy City file. Now the first one, because they came from the SAO Easy City file, I called all these, I put the word table as part of their name, because it came from that table that doesn't change, the SAO Easy City file. Students can call it whatever they want, I don't really care. So the first of those three arguments is what I called ID table. You can call it whatever you want, but it has to be declared as 6,893 strings, each 10 characters long. Again, because of the way C works with memory, you have to do it the same way. And so these will be the station identifiers that you read in from the SAO City file. Now you already did this back on assignment 12, as you might recall. Okay, you already have an array with a name similar to this or whatever that already is 6,893 station identifiers. Lat table and lawn table also come from data that is stored in the SAO Easy City file. Again, you probably already have those, depending on exactly what you did when you read the SAO Easy City file, but you probably already have two floating point arrays that each contain 6,893 floating point numbers. One is a list of all the latitudes of the stations, and one is a list of all the longitudes of all the stations. So row I of that table will contain a station identifier and a latitude and a longitude associated with that station identifier. So arguments 3, 4, and 5 are all information that come to us from the SAO Easy City file. I have a misprint there. I said SAO City, but it's SAO Easy City. Okay. Again, that means you have to have declared those arrays, and you have to have filled them up higher up in the program before you get to the Barnes objective analysis call. Because these arrays have to be filled with data. They have to be declared this size, and they have to be filled with data when you read the SAO Easy City file. Okay, the sixth argument. The sixth argument is just the radius of influence that you want to use for the Barnes objective analysis. And it is in units of degrees. And so it's a floating point number. Like in this example here, I used 4.0 as my radius of influence. So any point within 4 degrees of latitude or longitude of our station will be included. Feel free to play with it. Once you have this working, it's actually kind of interesting to say, what would have happened if I used a bigger one? What would have happened if I used a smaller one? It will eventually, it's a little hard to tell that on this assignment because you're just going to be plotting numbers. When you have the contours working in the next assignment, it's actually kind of intriguing to mess with that radius of influence. You'll see how you can change the plot depending on the radius of influence you choose. The bigger the radius of influence, the smoother the contours get, but the less representative of reality they get. Whereas the closer the smaller the radius of influence, the contours get crazier, but they also reflect very small changes in the temperature between stations. So radius of influence, 4 is a good typical value for this assignment. That's no problem whatsoever. The seventh argument is this n. N is going to be the number of observations that were in the current underscore SAO WXP file. So when you read the current underscore SAO WXP file before, you didn't worry about actually keeping track of how many there were. You just let it run while not end of file. Now you need to have a little variable, let's just call it n, but you can call it whatever you want, that you set to 0 before you start reading the current underscore SAO WXP file. And every time you read a line from that file, just make n equals n plus 1, or n plus plus would be more elegant. So that when you get done reading, once you have hit that end of file, n is how many lines there were. How many observations were there in that that current underscore SAO WXP file? Neat. Why does Barnes need to know that value? Because it needs to know how many rows of those first two arguments. Remember, ID had 10,000 rows, but you didn't necessarily use them all. You only used the first n of them. And temp, which had 10,000 floating point numbers in it, you didn't really necessarily use them all. You only used the first n of them. So the Barnes objective analysis does need to know how many stations reported that hour. And that will be n. Okay, next. Grid latitude and grid longitude. Grid latitude and longitude are two arrays. Again, you can call them what you want, grid lat or grid lon or whatever. And they have to be declared to be floating point numbers, and they have to have rows in them. Whatever you've decided is how many rows you want to have in your output. How many rows there'll be on your map, and how many columns there'll be. It has to be the number of columns of grid latitude and grid longitude. Now, what are these values? Grid latitude and grid longitude are the latitude and longitude of every grid point on your final plot. Remember when we were looking on that map of South Dakota and we were working with that location that was in southwest South Dakota? We need to know what its latitude and longitude is. How do we know that? Well, you already know that you have a northernmost and a southernmost and an easternmost and a westernmost as part of your how you are doing your map projections and so on. Northernmost is row 0, right? The latitude of northernmost is that 0th row of your array, and southernmost is the num rows minus 1th array row of your array. Anything in between is just interpolation. Oh. Same with the longitudes. You already know that you have a westernmost. That is the 0th row of the 0th column of your arrays. Its longitude is westernmost. The last column of the arrays, the num cols minus 1th row, a column of the arrays, is easternmost. That's its longitude. Any place in between, that's interpolation. Oh. So what you're going to have to do is do some kind of interpolation as a way of deciding what is the latitude and longitude of every one of my grid points. Neat. We're going to get started with that by having you guys take on that challenge yourself as to how to do that interpolation. Now, there's an appendix at the back of the book all about interpolation. If you're not like loving interpolation or whatever, okay, because I mean sometimes that's something that you haven't done since like high school and people get a little freaked out about that. Okay, but what's going to happen is if that becomes something you can't get done on your own, and don't get me wrong, defining the values of grid latitude and grid longitude is not like a huge thing. That's going to be, I don't know, 4 lines or something in your program. But it can be a challenge. Okay? So if you can't get it to work, I will provide you with code that can compute grid latitude and grid longitude. Okay? Based on your values of easternmost, westernmost, northernmost, and southernmost. And num rows and num columns. But it's not actually the end of the world. It's just interpolation. And you're going to be doing tons of interpolation in the last assignment. So frankly, getting a handle on how interpolation works is not going to be such a bad idea anyway. All of these things so far, ID, temp, ID table, lat table, lon table, the radius of influence, and grid latitude, grid longitude, are all pieces of information that the Barnes objective analysis needs. They're inputs. The 10th argument is the output. The Barnes objective analysis will change the values in an array, which I'm calling grid here. You can call it whatever you want, like output grid or something might be better, or OA grid for objective analysis grid or something like that. That might be better too. Whatever. It has to be declared to be a floating point grid. It has to be declared to have num rows in it and num columns in it. Okay, that's why those pound-defined constants are pretty nifty, because if later you want to have more rows and more columns, you just change it in one place at the top of your program. This is where the output is going to get put. These are the values that come back from objective analysis, where that grid will now be filled. At that latitude and that longitude that you get from grid latitude and grid longitude, you now know what, at least what objective analysis thinks is the temperature at that location. See how just getting this to work is enough? Actually writing the math of the objective analysis scheme is not necessary. Here we go. Let's think about assignment 14. You're going to start with the assignment stuff that you had from assignment 12 and kind of make some modifications and then add some new stuff. Just like before, you have to open the graphics window, you have to draw the maps, clipped maps. You know, read in everything that you get from the SAO Easy City file, like all those station identifiers and the latitudes and the longitudes, which you're going to put into arrays that have 6,893 elements in them, which actually you did before, I believe, in assignment 12. Then you're going to read through all the observations that are in the current _SAO WXP file and decode them and so on. But instead of right away plotting them, what you're doing is you're putting them into a table, into arrays, where you're putting, in something called like ID, you are storing the station identifier, and it's, in row I, you're putting the station identifier, and in row I of a, like just say temporary or temperature or something array, you're putting the decoded temperature and so on. Those arrays have up to 10,000 rows in them, but you aren't going to need anywhere near 10,000. You're going to just need n of them, depending on how many stations are actually in there before you hit the end of file. Alright, so you still haven't drawn any weather data up there. Then, what you're going to have to do is set up all your arrays of like grid latitude and grid longitude and what the output grid will look like and so on. That's going to hold all this objectively analyzed stuff. You're going to have to determine the latitude and longitude of every grid point in there for your grid latitudes and grid longitudes. And you're going to have to implement, but not write, just implement the you don't have to write barnes.c, you just have to, put barnes.c. I'd recommend importing it into your metcalc.c library. Some students just go ahead and pound include it themselves. Use another pound include and then just make it, home / whatever your login is / barnes.c. That also works. However you want to do it is fine with me. Then you implement that Barnes objective analysis code that I give you, and you plot the values at each point. What do I mean there? What I mean is I want you to actually make a map that looks like this. Okay? You know the latitude and the longitude of every one of these points. And now you know a temperature at each of those points. Well, at least you know what are the Barnes objective analyzed values at that point, the estimates at that point. So then, you've got a grid latitude, so for row I, column J, you know its latitude and its longitude from grid latitude and grid longitude. Use your transform latitude to change that latitude to a Y. use that transform longitude function to change that longitude into an x. Then take that x and y location and clip it, because I don't want values outside of my map here. I just want them inside the map. And once I've clipped it, then gprint it. At gprint at my location, this xy, gprint the value that Barnes objective analysis just gave me in my grid array. Ooh, it's fancy. It's fancy. Honestly, this is not that many lines different from assignment 12. If you're take assignment 12, copy it over, call it assignment, what are we on, 14, because I don't think we did 15 this year. I'm sorry, I don't think we did 13 this year. Copy over 12 to 14 and start making the changes here. But if you're making like hundreds of changes, you're not doing it right. This is only going to be, you know, like, oh, here we used to plot it, remove that because now we're not plotting it, instead put it into an array. Okay, yeah, it's taking a line out here and putting a different line in here. Oh, well then we're adding this, I mean, most of the stuff that's in the subjective analysis stuff, you already are doing. Really, it's this computing grid latitude and grid longitude that's a little bit of a pain. And yeah, that's it. This program wouldn't have to be much different than assignment 12. But I understand it's a challenge. I understand getting all of this stuff to be correct, to have the right values in each of those 10 inputs to the Barnes function is plenty to get you guys to get this to do. Alright, this is really cool. And this has to work in order to move on to assignment 15 where you're going to be contouring this. That's going to be so cool. Alright, take a stab at it. Please let me know if you're going to have questions. Please let me know if you have questions. This is a very good example of the kind of program where you don't want to be tearing everything apart and writing tons of code. Okay? Make little changes to the program assignment 12, which is already working. Make sure it keeps working. Make little changes, compile it. Make little changes, run it. Make sure it's working before you take apart your assignment 12 and have done enormous damage. Alright. I think that's everything that you need. Please let me know when you have questions. This has been Dr. John Schrage.